Good day. Today we're going to discuss the test of hypothesis. Let's assume a superintendent of a school get a report. The national mean NATA score is 91. Additionally, imagine that his division's students have a mean of 96. Could the, could the superintendent come to the conclusion that his students perform better than the average student? As we begin to think about it, we might be tempted to agree because, of course, 96 is greater than 91. But keep in mind that the method of selecting samples might differ from the mean of the population, depending on where the sample are picked from. Thus, it may be argued that the discrepancy between the means is not genuine, but just a result of sampling error. In this presentation, we will discover how to provide an answer to that question using statistics that provide context for hypothesis testing. You'll discover how to address several issues of this sort by applying statistics, which are discussed in the hypothesis testing theory. Okay, to start, uh, what do we mean when we say hypothesis testing? So, researchers are eager to tackle a multitude of issues. Okay, so scientists may want to learn if the earth is warming. Okay, when determining if a few medicine works, a doctor would want to know if it will reduce their patient's blood pressure. Teachers might want to check if a new teaching method is more effective than the old approach. If a retail merchant is launching a new line of clothing, they may want to know if customers like a specific hue. Manufacturers also in the auto industry are looking at whether the seatbelts might help prevent the severity of injuries after a crash. These types of questions can be addressed through statistical hypothesis testing, which it is the decision making, okay, a decision making process for evaluating claims about a population. In hypothesis testing, the researcher must define the population under study, state the particular hypothesis that will be investigated, give the significance level, select a sample from the population, collect the data, perform the calculations which is required for the specific statistical test, and reach to a conclusion. So that's what we call as hypothesis testing. Okay, so let's start. Let's go to first testing the difference of two variances. Okay, so statistical analysts, okay, are concerned with examining two standard deviations. For instance, there is a disparity of monthly temperature fluctuation between two cities. An investigator may be interested in examining the difference in cholesterol levels between men and women in another scenarios. So these examples are testing the difference of two variances. Okay. Now, this would be the formula for the F test. So we have here F is equal to, okay, this one, okay, this is the variance of one sample, and then over the variance of the other sample, where the larger of two variances is placed in the numerator regardless of subscript. So take note, your numerator here should always be greater than the denominator. The F tests have two terms of degrees of freedom, that of the numerator, n sub 1 minus 1, and of that denominator, n sub 2 minus 1, where n sub 1 is the sample size from which the larger variance was obtained. So the F test is used to compare the standard deviations of two variances. Okay, we have to bear in mind that the F test, okay, uh, there is a difference between F-test and chi-square, which compares the sample variance to the population variance. So in this case, we are not comparing to the population variance. So if two independent samples are selected from two normally distributed population in which the variances are equal, okay, and if the variances, okay, the variance 1 and variance 2 are compared as the sampling distribution of the variance is called F distribution. Okay, so this would be the characteristics of the F distribution. Okay, so the values of f cannot be negative. Of course, it cannot be negative because we are talking about variance. Variance is squared. The variance is, uh, take note that it is the square, diba? In the formula. Okay. Because variance are equal, always positive or zero. Okay. The distribution is positively skewed. Okay, the mean value of the f is approximately equal to 1, and the f distribution is a family of curves based on the degrees of freedom of the variance of the numerator and the degrees of freedom of the denominator. So when we are finding the f test value, the larger of the larger of the variances is placed in the numerator of the formula. This is not necessarily the variance of the larger of the two sample sizes. Okay. So this would be the assumptions. So the assumptions, the population from which the sample were obtained must be normally distributed. Okay, and the samples must be independent from each other. Okay, so the larger the variance should always be placed in the numerator of the formula, regardless of the subscript. So we have to bear that in mind. And then for two-tailed tests, the alpha value must be divided by 2 and the critical value placed on the right side of the F curve. So if the standard deviations instead of the variances are given in the problem, they must be squared for the formula for the f-test. Take note that this, okay, this formula is stands for variance. Now there are some problems na the given is standard deviation. So if that would be the case, then we are going to determine first the variance. Okay, when the degrees of freedom cannot be found in the table, okay, later on we're going to discuss the table, the closest value of the smaller size should be used. Okay, so let's have example. Okay, so the regional supervisor in mathematics hypothesizes that the variance in the math MPS of Rizal division is greater than the variance in the Mabini division. At alpha equals 0.10, is there enough evidence to support the hypothesis? So here we have uh, the data. For the result division, we have 36.8, 72.4, 60.5, 73.5, 61.2, 40.1. And for the Mamini division, we have 60.7, 42.7, 51.2, and 38.6. Clearly, in this example, this is a sample. Okay, so the mean, that means that's the data is taken a sample from the Rizal division and another sample from the Mabini division. So to determine or to answer this kind of problem, we have this solution. So to solve this one, let's have, okay, for the solution, okay, so step one, okay, step one, what we are going to do is we are going to state the hypothesis and we have to identify the claim. So in this case, we have here that the mathematics supervisor, regional supervisor hypothesized or hypothesizes that the variance of the math MPS of Rizal division is greater than the variance of the Mabini division. So in this case, if this would be the hypothesis, the claim, okay, technically this is the claim of the regional supervisor. So in this case, if let's say you have mu1, okay, mu1 is greater than mu 2, okay, in this case, this would be our alternative hypothesis. So this is our alternative hypothesis, which is the claim of the regional supervisor. Why it is the alternative hypothesis? Take note that when we talk about null hypothesis, it is always stated something like there is no significant. Okay, when we say there is no significant difference between the variances of the two division, it means to say na there are no difference, they are equal. So the variance of the Rizal division is equal to the variance of the Mabini division. So if that would be the case, okay, so this would be our null hypothesis. So for our null hypothesis, we have mu1 is equal to mu2. Okay, mu1 and mu2 is our mean. But take note, since the problem here is variance, therefore, our real hypothesis would be from the alternative, then we have the variance of the Rizal division is greater than the variance of the Mabini division. Therefore, our null hypothesis would be the variance of the Rizal division is equal to the variance of the Mabini division. So this would be our null hypothesis. And of course, this is the claim of the regional supervisor. Okay, now step 2. What would be the next step? So since we already identified the hypothesis, we are now going to compute the test value. So we are going to find the variance of each group. Okay, so let's migrate to Excel. So this is now the data. Okay, so take note that the formula for the F test is that we are going to get the ratio between the variance of the two division. So in this case, we are going to get the sample variance. So you have var, sample variance, and then highlight this one, then equal. So the variance for the Rizal division is equal to 246.38166667. Okay, while the variance, of the Mabini division, okay, is equal to 95.8733 and so on. Now take note that to get the F value, okay, in getting the F value, we are going to get the ratio between these two numbers. Then take note that our numerator must be greater than the denominator. In this case, since the variance in the Rizal division is greater than the variance of our Mabini division, our numerator must be the Rizal division and the denominator would be the Mabini division. So we have Rizal divided by the Mabini. And our variance would be, not variance, the F test would be 2.5698. Round off to 2.57. Okay. So in this case, we could now have here that our F, the computed F test, so this is computed, okay, our computed F test or the F value, computed F value, okay, since we have the formula of, we have the sample variance of the Rizal over the sample variance of the Mabini, okay, is just equal to 246.38 over 95.87, which is just equal to 2.57. So that is our computed f value. Now, since we are going to determine whether they have the is there enough evidence to support the claim of the original supervisor. So if this would since we are going to determine whether there is enough evidence, we are going to get the tabular value, the tabular f value. Okay. To get in getting the tabular f value, we're going to use the table. Okay. Now, to determine the tabular value, let us first set the degrees of freedom. Okay. So since we have numerator and denominator, then we are going to determine first the degrees of freedom in the numerator. Okay. Now to get the degrees of freedom in the numerator, we only have formula of n sub 1 minus 1, where n sub 1 is the number of elements in our samples in the numerator. And of course, for our degrees of freedom, okay, of freedom in the denominator, that would be equal to the number of elements in the denominator minus 1. So as we can see here, okay, in our numerator, which is the result division, we have 6. Therefore, we have 6 minus 1 equals 5. And then for the denominator, we have 4. So we have 4 minus 1 equals 3. These are important numbers in locating the tabular f value. Okay. So this would be our tabular f value. So as we can see here, we have the alpha level. Okay. The alpha level is uh, 0.01, and then we have degrees of numerator and then degrees of denominator. Now, if you can still remember, our numerator is equal to 5. So this would be the numerator. So 5. And the denominator is equal to 3. Now we're just going to locate the number intersecting with these. Okay, with this line. So in other words, our tabular f value is equal to 5.31. So our f, okay, for the tabular, say this is tab, is equal to 5.31. In this case, by the way, this example is the example of one-tailed test because our null hypothesis, not the null, our alternative hypothesis has a comparison symbol of greater than. So if the comparison symbol in our alternative hypothesis would be greater than or less than, then that is a one-tailed test. If the comparison symbol of our our alternative hypothesis would be not equal to, then that would be two-tailed test. So why is it important to know? Okay, it is important to know because if we are going to draft, okay, a graph, okay, assuming this is the graph. So this, since f test is positively skewed, so something like this. Okay. So if we are going to plot the tabular value 5.31, most likely, okay, so this is the 5.31. So anything, if the value lies within this shaded portion, then we are going to reject the null hypothesis. But if the value lies here in non-shaded portion, then we are going to accept the null hypothesis. In this case, our computed f value is 2.57, so somewhere here. So 2.57. So in other words, since for our number 4, since the computed f value is lesser than the tabular f value, then our decision is we are not going to reject the null hypothesis. So our decision, not reject or do not reject the null hypothesis. Take note that our null hypothesis is there is our null hypothesis is there is significant different. There is no significant difference on the variances of the two division, which is the Rizal division and the Mabini division. Since here we are not going to do not, okay, it must be do not reject. Okay, do not reject the null hypothesis. So since the in our step 4, uh, we are not going to reject the null hypothesis, it implies, okay, that we are going to reject the alternative hypothesis. So since we are going to reject the alternative hypothesis, which is the claim of the regional supervisor, then for our interpretation here, we could now say that there is uh, not enough evidence to support, okay, the claim of the regional supervisor in mathematics. So this would be our interpretation. This would be the manner of our discussion when we are going to report. Okay, so there is not enough evidence to support the claim of the regional supervisor since the computed p-value is less than the tabular f value. And it implies that we are not going to reject the null hypothesis, which implies also that we are going to reject the alternative hypothesis. Since the alternative hypothesis is the claim of the regional supervisor, therefore we have statistical evidence not to support or to reject the uh, hypothesis of our regional supervisor in this case. Now, this is how we are going to solve manually. But we also have we also have technology in which we are not going to do manually. So let's have Excel. Okay, let's go back to our Excel. So here we have our division, Rizal division, and Mabini division. So using the megastat, we can now compute or we could now determine if the difference is if there's significant difference in the variances of the two division. So we go to add-ins and then megastat, and then we are going to have hypothesis test, and then let's have compared to independent groups. Okay, in our group 1, so our group 1 is the Rizal division, and our group 2 is the Mabini division. Now take note, our hypothesized difference is 0 because our variances, okay, in our uh, null hypothesis, they are equal. So if they are equal, if we hypothesize in our alternate null hypothesis as equal, then if we are going to subtract the numbers, then it's equal to 0. The alternative is not equal. Okay, they are not equal. They are greater than. Okay, if the because it is a one-tailed, okay, one-tailed test. Okay, if the alternative is not equal, meaning it's two-tailed. If it is greater than or less than, then that is one-tailed test. Now take note here. Okay, we have tests of equality of variance. Okay, so we're going to check that one. And then take note in the problem that is the alpha is 0.10. So we are going to change the confidence interval into 90. And then, okay. Okay, click no. And let's wait for the result. So here, we have here, okay, the result. So as we can see, let's try to make it larger. Okay, this would be the focus of our problem, the F test for equality of variance. So here the variance of our result division is 246.382. Okay, so round off to 3 decimal places. And the variance also of our Mabini division is 95.873. Okay, round off again. And then the variance is equal to 2.57, which is also the same with what we got in our previous manual computation. And the p-value is 0.4672. If the p-value is greater than the established p-value in the problem, remember the problem that the alpha there is 0.01. If the p-value is greater than the level of significance, then we are not going to reject the null hypothesis. Okay, take note that if the p-value is greater than the alpha level, we are not going to reject the null hypothesis. If the p-value is less than the alpha level, then we are going to reject the null hypothesis. In this case, uh, we are not going to do the rigorous manual computation, but rather we are just going to input the data and let the Excel do its work. So this is how we are going to use the mega stat. Let's have another example. Okay, we have here schools were randomly selected from the list of 50 schools in the division. Is there sufficient evidence to conclude that the variance of the population in East cluster is greater than the variance of the West cluster at alpha equals 0.05? So our level of significance here is 0.05. Okay, let's try to solve manually. Okay, if we are going to solve this manually, our first step, okay, for our solution, our step one would be we are going to state the null and alternative hypothesis. Okay, as what I have mentioned in the previous discussion, in the previous slide, our null hypothesis is always, okay, the variance of, let's say, East cluster is equal to the variance of the West cluster. Why we have this kind of mathematical equation or mathematical statement? Take note that the null hypothesis in this case would be there is no significant difference between the variances in the population of East cluster and the West cluster. That is our null hypothesis. Now, if we are going to translate that statement into mathematical statement, since there is no significant difference, then they are equal with each other. Okay, in other words, our alternative hypothesis here, okay, okay, if we go back to the claim, okay, here in our example, we have there is the variance, okay, in the East cluster is greater than the variance of the West cluster. So in other words, okay, that would be our alternative hypothesis greater than the variance of the west cluster. And this would be the claim. Okay, take note, this is the claim in our problem. And take note also that the alpha, the level of significance is 0.05. Okay, next step, we are going to compute. We are going to compute, okay, the uh, computed f value. Okay, let's try to have the computed f value. Okay, take note that the formula for the computed f value is that we have the, okay, variance of the east cluster over the variance of the west cluster. So let's try to move, or let's try to migrate to Excel. So this is the Excel format of the data in the problem. So what we're going to do here, let's try to determine first the variance of the east cluster. Now take note in the problem, it's clearly stated there that there is a sample from the east cluster and sample of the west cluster. Since it is stated there that it's a sample, then we are going to have the variance of the sample. Okay, and then, okay, highlight there. And then here, the variance. Okay, so first let's try to determine which among or which between the two is has a larger variance. So clearly here, we could have the east cluster is greater than the west cluster in terms of its variance. Therefore, our numerator would be the east cluster and the denominator would be the west cluster. Take note that the F test, there should be greater numerator compared to the denominator. So in this case, we have this one, the variance of the east cluster divided by the variance of the west cluster, which is equal to 9.80. So take note, we have here, you have 12,367.905, and here we have 1,261.90. Okay, so let's try to write that one in our solution. So we have, okay, the variance in the east cluster, since it's much greater compared to the west, so it should be placed in our numerator. So you have 12,367.905 all over. We have 1,261.90. Okay, which is equal to, as what we have got in our Excel, we have 9.80. Okay, so this would be our computed F value. So let's try to have the tabular F value. So to determine our tabular F value, we have first to determine the uh, degrees of freedom in the numerator and the degrees of freedom of the denominator. So take note that the formula for this is you have n sub 1 minus 1. And for the numerator, since the numerator is east cluster, there are 7. Okay. In this case, you have east cluster 1, 2, 3, 4, 5, 6, 7. So 7 minus 1 is 6. And for the denominator, we only have 1, 2, 3, 4, 5, 6. And since it's 6, then we have 6 minus 1 equals n sub 2 minus 1 is equal to 6 minus 1 equals 5. Take note that the 6 here is not taken from the results in above. It is taken from the number of data in our west cluster. So 1, 2, 3, 4, 5, 6. And 6 minus 1 is equal to 5. Now let's go to our table. So for the numerator, okay, 6. And the denominator is 5. So let's try to have Okay. So this would be the computed F value. So the tabular F value is equal to 4.95. So if we are going to draw that one in the graph, so since it is a positively skewed, so something like this. Okay. So for our tabular, so this would be our tabular. So that is 4.95. So in this case, and the computed is 9.80. So somewhere here. Okay, so this is 9.80. So as what I have mentioned in the previous discussion or in the previous slide, that the computed, if the computed F value lies within this shaded portion, then we are going to reject the null hypothesis. In other words, for our step 4, we could have, since the computed F value is greater than the tabular F value, then we could say that we are going to reject the null hypothesis. That implies that we are going to accept or do not reject the alternative hypothesis. Now, take note that in this case, the alternative hypothesis is the claim, okay, in our problem. Therefore, we could now say here, for our step 5, we could now say here that there is enough evidence to support, okay, the claim of the researcher. Okay, so what is the claim of the researcher? The claim of the researcher is that the variance of the population in the East cluster is greater than the variance of the West cluster at alpha equals 0.05. Now, let's try to have that one in the mega stat. So this is the megastat. What we are going to do, we go to add-ins, megastat, and then we go to hypothesis test, and then we have compared two independent groups. In this case, our group 1 would be the East cluster, and our group 2 would be the West cluster. Okay. Here, the hypothesized difference is 0, and then our alternative hypothesis is, as we can have in our null hypothesis, it is greater than. Okay. And then since the alpha is 0.05, then our confidence interval is 95%. And then we are going to click the test of equality and then okay. Okay. Let's wait. So here we could have say here that the F test, we are going to focus only to this portion, the F test. Since the F test of equality of variance is, we have here the results. The variance of the East cluster is 12,370, 367.90, round off. Let's just round off. And then the West cluster is 1,261.90. And then the F value is 9.8, which is also the same of what we have computed, okay, in our manual computation. And here, as we can see here, the cell for the p-value is shaded. If the cell for the p-value is shaded, it means to say that it is less than 0.05. Since the p-value here is less than 0.05, then we are going to reject the null hypothesis. So this is the easiest way to determine the significant difference between the variances of two samples. So that's how we are going to do using the mega stat. So we already have the difference of the two samples of variances. So let's have testing the difference between the two means of independent samples. So the population standard deviation are not known in this case. Okay. Uh, in the cases, the t-test is used to test the difference between the means when the two samples are independent and when the samples are taken from the two normally or approximately normally distributed populations. So the samples are independent samples when they are not related with each other. Okay, so this would be the formula of the t-test for testing the difference between the two means, the independent samples. So we have here the variance are assumed to be equal, then this would be our formula. So this is our formula. The t equals the quantity. Okay, we have the mean, the sample mean of the first group minus the sample mean of the second group minus the quantity. Okay, you have the population mean of the first group minus the population mean of the second group all over the square root of the variance of the first sample over the number of elements of the first sample plus the variance of the second sample over the number of elements of the second sample. So again, this would be the formula if the variances of two samples are assumed to be unequal. So they are different from each other. Okay. But this would be the formula of the t-test if the variances are assumed to be equal. So when can we say that the variances are assumed to be unequal or assumed to be equal? We are going to use the F test, the what we have done in the previous discussion or the previous slide. So first we go to the F test so that we could now determine whether we are going to use this formula or the other formula. Okay, so where the degrees of freedom are equal to the smaller of n minus 1 or n sub 1 minus 1 or n sub 2 minus 1. Now, what does it mean? Okay, we are just going to look for the smaller sample size, and then we are going to use that one as our degrees of freedom. Okay, let's have an example. So we have here the regional supervisor in mathematics hypothesizes that the mathematics MPS of Rizal division is greater than the Mabini division at alpha equals 0.1. Is there enough evidence to support the hypothesis? So take note that we already computed here we already computed the F test here. So the F value. Now, in our previous discussion, clearly we have the variance of these examples are not equal with each other. So since they are not equal with each other, then we are going to use the formula, the first one, to compute, to determine whether there is significant difference between the mean, okay, of the Rizal division as compared to the Bambini division. First, we are going to set the hypothesis. So for our step one, we're going to have the hypothesis for our solution. So here, our null hypothesis would be, for we have the population mean of the Rizal division, okay, is equal to the population mean of the Mabini division. And for our alternative hypothesis here, okay, we could have the uh, the mean or the population mean of the Rizal is, as we can see here, greater than the population mean of the Mabini division. And take note, this is the claim of the researcher or the regional supervisor. Next is we are going to compute the test value for number 2. Step 2 is we're going to use the formula T is equal to, you have the sample mean of the first group minus the sample mean of the second group minus, you have the population mean of the first group minus the population mean of the second group all over, we have the square root of the sample variance of the first group over the number of element of the first group plus the sample variance of the second group over the number of elements of the second group. Okay, let's try to go to our Excel. Take note from our discussion previously, this is the sample variance of the Rizal division, and this is the sample variance of the Mabini division. What we are missing here is the sample mean. So to get the sample mean, we are just going to get the average. Okay, the average of these numbers, and then the average of these numbers. Okay, so for our mean for the result division, okay, so we are now going to use the formula. So this would be the t test. Okay, so we have, take note, okay, equal sign. Okay, let's have, okay, 3 open parentheses. We have the first, the mean, the sample mean, minus of the first group minus the sample mean of the second group. Okay. Minus, take note that our population means, since in our null hypothesis it's stated there that there is no significant difference between the mean of the population mean of the two groups, then it means they are equal. If we are going to subtract equal quantities, it's equal to 0. Okay, close. Okay, divided by, okay, divided by, you have there, okay, the square root. Okay, let's have this one. So you have square root, you have the square root of, you have uh, the variance, okay, open parentheses, the variance divided by, okay, number of elements in the result division. We have 1, 2, 3, 4, 5, 6 divided by 6, okay, plus, okay, you have now this variance divided by 4. Okay, and then let's close again. Okay, and then another close. Okay, so we found type of formula. Correction, yes. Okay, so the t value is equal to 1.13. Okay, so we are going to substitute our formula, our value here. So you have the sample mean of the first group which is the result, is equal to 57.42 minus the sample mean of the second group, which is the Mamini division. You have 48.3 all minus, okay, here 0. The answer here is 0. Okay, all over, you have the square root of, you have uh, the first group is 246 point, let's say 38, all over the number of samples in the result division is 6, plus you have 95.87. So 87 over 4. Okay. From our Excel, that is equal to 1.13. So in other words, our computed t-value is equal to 1.13. Okay. So let's try to determine now the tabular t-value. So for the tabular t-value, we are going to determine first the degrees of freedom. Now take note from the discussion that we had in the previous discussion, in the previous slide, that the degrees of freedom would base on the least number of elements of the samples. Between the Rizal division and the Mabini division in this example, the least number of sample is the Mabini division. So we have n minus 1 is equal to 4 minus 1 equals 3. Okay. So, in our table, so this would be our table. Okay, so we only going to have our one tail. So, the reason why we have one tail is because the alternative hypothesis in the problem pertains to inequality, greater than. So, since the inequality symbol there, or the comparison symbol is greater than, then we are going to use the one tail. Okay, so greater than, less than, that would be one tail. But if the alternative hypothesis has the comparison symbol of not equal to, then then that problem pertains to two-tailed test. Okay, now the alpha is 0.01 in the problem. So, okay, 0.01. So this column, okay, is our basis. And then the degrees of freedom is 3. Then we are going to have the 3 here. So in other words, our tabular value is 1.638. So here we could have the tabular t-value is equal to 1.638. So if we are going to draw that one, okay, if we are going to draw that one in our normal curve, it's not, the curve here is not the same with the curve in the f-test, because in the f-test, they are positively skewed. Here, it should be normally distributed. So assuming that this is the graph of the normally distributed, and of course, this one is our mean. So this is the mean. Okay. Now, the tabular is 1.638. So the mean should be equal to 0 because it would be equal to the standardized. Okay. So if the mean is 0, then we have here. So this would be our 1.638. So if the value lies within this shaded portion, then we are going to reject the null hypothesis. However, the computed t-value is 1.13. Therefore, it is placed somewhere here. So it is equal to 1.13. In this case, we could now have for our number 4, okay, in this case, the computed, the computed t value is less than, okay, is less than the tabular value, okay, which implies, okay, that uh, we could have do not reject the null hypothesis. Since we do not reject the null hypothesis, it implies that we are going to reject the alternative hypothesis. Then take note that the alternative hypothesis is the claim of the regional supervisor. Then we could now have for our number 5, okay, for our interpretation, then we could say that there is not enough evidence or statistical evidence, oops, to support the claim of the regional supervisor. Okay. And take note that the claim of the regional supervisor is that the mathematics MPS of the Rizal division is greater than the MPS of the Mabini division. Now, this is how we are going to do if we are going to do it manually. But how we are going to do it if we are going to use the Megastat, the Excel. Okay, so let's move to Excel. So this is now the Excel. What we're going to do, we are going to go to add-ins, Megastat, and then we're going to use the hypothesis test, and then compare two independent groups. Okay, so in this case, okay, so our group 1 would be the Rizal division, and our group 2 would be the Mabini division. Now, the hypothesized difference is 0, but in this case, the alternative must be greater than. Okay, and then we're going to use the unequal. We are going to click here the unequal variance because that's what we did in that's the result in our F test. Okay, and then the confidence interval is 95 because the alpha level is 0.05. Okay, and then click OK, and then click no. So this would be the result. So here we have the mean of the two divisions, the standard deviation, the mean. Okay, and the n. Okay, so degrees of freedom is 7. But take note that what we have did here is the degrees of freedom is taken in the least number of samples, which is 4. Okay, so here our difference, we have standard error, hypothesis difference. The t-value here, clearly, we have here the t-value is 1.131, which is the same of what we obtained in our in our manual computation. And the p-value here, as we can see here, the p-value is greater than the alpha level. So since it's greater than the alpha level, then we are not going to reject the null hypothesis. And since we are not going to reject the null hypothesis, we reject the alternative hypothesis, which is the claim of the regional supervisor. Okay, so let's have another example. So here, the schools were randomly selected from the list of 50 schools in the division. Is there sufficient evidence to conclude that the population of East, okay, cluster is greater than the West cluster at 0.05 level of significance? Okay, so clearly we have here that the p-value is the alpha level is 0.05. But in this case, okay, although the data is taken is the same with what we had in our previous previous presentation, which is in the difference of the two variances. So in this case, it's not the variance but the mean. Okay, so what we're going to do here, we are going to compute, okay, to determine if the difference of the population from the 50 samples, from the list of 50 schools in the division, the East cluster and the West cluster, they are significantly differ from one another. Take note that the claim here is the East cluster is greater than the West cluster. So for our for our hypothesis, for our solution, so our step one, we're going to determine the hypothesis. Hypothesis rather. So our null hypothesis would be, okay, the population mean of the first group is equal to the population mean of the second group. And of course, our alternative hypothesis would be, okay, this one, the claim. So the population mean of the first group, which is the East cluster, is greater than the population mean of the, okay, West cluster. Okay, so for number two, since in the previous discussion, we discovered that the variance or the variances of this example are assumed to be equal. So since we assume to be equal, then the formula that we are going to use for the determination of our t-test or t-value is, so our formula must be in getting the t-value, the computed t-value, is we have uh, the mean, the sample mean of the group 1 minus the sample mean of group 2 is subtracted by the population mean of group 1 minus the population mean of group 2 all over, you have the square root of, you have the number of elements of group 1 minus 1 times the sample variance of group 1 plus the number of elements of sample 2 minus 1 times the variance of the sample 2 all over, you have the sample number of samples of group 1 plus the samples of group 2 minus 2 times again the square root of 1 over the sample of group 1 plus 1 minus all over the sample of group 2. Okay, so let's proceed to our Excel. So this is the Excel. Okay. Now in this case, we already have the sample variance of the two groups. Then let's get the mean. So to get the mean of the first group, then we have equal sign, then average, open parentheses, highlight those numbers, close. And of course, we also have this one, average, highlight those numbers, and equal sign. Okay, so now we are going to have now the t. Okay, so to get the t value, the computed t value, now take note that we have the numerator. Okay, the numerator, okay, you have two elements in the numerator. You have the mu1, and not the mu, the sample mean 1 minus the sample mean 2 minus, of course, the sample, the difference of the population means, which is equal to 0. Close. Okay, so we already closed. Then let's have our denominator divided by, for the denominator, we have two square roots. So since we have two square roots, in this case, we are going to have, uh, okay, open parenthesis first. You have the square root, okay, the square root of the number of elements. Number of elements in the first group, we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So you have 7. Okay. So you have here 7 minus 1 times, okay, times the the sample variance of the first group, okay, plus, okay, to emphasize that there should be, there are two multiply first before they are going to add. So you have, okay, this case, then we have the second group, 1, 2, 3, 4, 5, 6. So 6 minus 1 times, not the A, it should be this one, B. Okay, let's change this one. This must be B11. It should be A11. Okay, close. Hmm. These whole terms, these whole terms would be divided by first by uh, you have n sub 1 is 7 plus 6 minus 2. Okay. Then again, okay, this group violet. Okay. It's already closed in here in the violet. Okay. Then multiplied by, okay, another close, and then multiplied again by the square root. Oops. Here multiplied by the square root of, you have two terms, 1 over the number of elements is of the first group is 7. Okay, close, plus you have 1 over the element of the second group, which is 6, close, and then another close and another close. Okay, so that's equal to 1.706. Okay, let's try to substitute in this formula. So we have, okay, here, so we have the sample mean, okay, of the first group is 209.71 minus the sample mean of the second group is 128.5 minus 0, okay, all over, then you have the square root of, you have n minus 1, n sub 1 minus 1 is equal to 7 minus 1 times the sample, and the variance of the first group is 12,367.905 Okay, plus you have 6 minus 1 times you have 1261.9 all over you have 7 plus 6 minus 2 times the square root of 1 over 7 plus 1 over 6. Okay, so that's the formula, which is equal to what we have computed in the Excel. You have 1.706. Okay, so in other words, our tabular, not tabular, our computed t value is equal to 1.706. This is uh, computed. Next step is we are going to determine now the tabular value, or the tabular t value rather. So for the tabular t value, our degrees of freedom, okay, we are going to base our degrees of freedom to the least number of elements. So in this case, the least number of elements is the west cluster, and then it has 6. Okay. So in other words, we have 6 minus 1 is equal to 5. Okay, let's now refer to our our table. So here, in this case, this is one tail test again. Okay, and then we have 5. So 1, 2, 3, 4, 5. So this is our tabular value. So our tabular t value, okay, for the tabular t value is equal to 1, not 2.015. Okay, now for our step 4, in this case, we're going to determine now whether we are going to reject the null hypothesis. So this is the, okay, uh, one tail test. Okay, so assuming this is our uh, normal curve, so our tabular, okay, since this is our 0, so most likely, okay, this is our uh, critical value, or the computed the tabular, so 2.015. Okay, so anything that lies here is reject. Okay, however, our computed is 1.706, so somewhere here, so 1.706. In other words, in our step 4, since the tabular, the computed t value is less than the tabular t value, therefore we are going to do not reject, okay, do not reject our uh, our null hypothesis, which implies that we are going to reject the alternative hypothesis, which is the claim of the researcher in the example. So in this case, okay, we could now say that there is not enough statistical evidence to support the claim, which is in this case, the claim is the population of the east cluster is greater than the population of the west cluster. Okay.